First off, good morning. I am Ashley Toten with the National Center for Defense Manufacturing and Machining, NCDMM, and the Program Manager for the AMNOW program. And I will be your host for today's AMNOW Polymer Challenge Industry Brief. A few important notes before we kick off the industry brief. At the end of the presentation, there will be an opportunity for Q&A. If during the presentation you have a question, please submit it in the Q&A space on your WebEx screen, and we will ask it during the Q&A session. We will do our best to get all the questions answered, so please ensure that you put it in the Q&A instead of the chat box. I would like to provide a little background on the AMNOW program. The AMNOW program is focused on developing and demonstrating a prototype AM digital supply chain system that enables bidirectional, secure digital transfer of contracting documents, technical data packages, and manufacturing process information between government agencies, DoD OEMs, and the industrial-based manufacturers. The program is focused on the sourcing, production, and delivery pieces of the digital thread. We are then digitally linking the sourcing, production, and delivery with the Advanced Manufacturing Intelligence Platform, or AMIP. The program has gone through multiple phases to get the supply chain integrated and to develop this prototype. I could go on and on regarding the AMNOW program. There's a lot of different aspects of the program, and I would encourage everyone to go to myamnow.com to learn more. And there will be a link provided on the last slide of today's brief. So without further ado, it is my pleasure to introduce Jennifer Coyne. Jennifer is the Associate Director of Programs for the Barnes Global Advisors. The Barnes Global Advisors are a partner on the AMNOW program and lead our engineering and technical efforts. Jennifer is leading the Polymer AMNOW Challenge, and Jen, I will now turn it over to you.
Good morning. It's a pleasure to speak with you all this morning. We've been pretty excited about bringing this challenge to you all today. With me today is Nat Frampton. He'll also be presenting some of the data and to field questions about the data and the scope of the project is Dr. David Prahl. So with that said, I'll go ahead and jump into the challenge here today. So I guess the background of the challenge, or we'll call it a problem, these desktop 3D printers are widely available and incredibly affordable, but they're rarely used to make anything beyond prototypes and toys and hobby level things. So the question or the hypothesis is, could we apply in-situ monitoring and low-cost sensors to a build and have more confidence in the quality of material extrusion polymer parts that are made on these desktop printers? So that's the premise with which we started this challenge. The opportunity now is we have produced several parts. It'll probably be over 15, probably well over 15 by the time we're done, but they're still in process, made from PETG, on material extrusion desktop 3D printers. In particular, they're made on Prusa machines. And these Prusa machines were, they're at Colorado State University, and they are equipped with in-situ monitoring and low-cost sensors. So they've done that aftermarket and added additional sensors onto the printers to make them more functional and understand what's going on during the builds. So what we did was we intentionally introduced anomalies into some of the parts, not all, and we are now seeking people with experience in data analytics or interest in data analytics experience with material extrusion to review the data and identify the anomalous parts. So the objectives of this is really going back to that problem, that hypothesis. Is it feasible to use AI or data analytics to find anomalies in situ data sets and correlate them with actual part quality? And really, we want to stimulate the development and discussion of AI algorithms for finding anomalies in situ data sets with the melt extrusion, material extrusion process and within the 3D printing community. And we really want to eventually, the end goal is create motivation for the industry machine providers to incorporate this data collection and maybe these low-cost sensors into their product features to enable this, so it's not all aftermarket and people have a common way of evaluating part quality. So the overview, there'll be 2 phases of this project. The first phase is all the manufacturing data. It's I'll describe that in subsequent slides here. And then the goal would be identify which of the parts in the test are anomalous. And then phase 2 will give additional data, which is test data or leak data, and we'll ask you to identify the leak location. There is a up to $20K award that is available to participants who successfully complete the project. Okay, the scope of the project, and you can see some of the pictures here. Again, over 15 builds, and there will be identified control parts for you to work with, so you'll know what good is. You'll have additional builds, which some will have intentional anomalies and some will not, and we will not tell you which ones have them and which ones don't. That's part of the challenge. And then in addition, in the phase 2 part, there's this testing portion, which you'll see on the left, this picture here. Each part is pressure tested by filling the part with compressed air at 1 psi, sealing it off, and allowing the pressure to slowly decay over time. Each part did leak, but there's different pressure curves that are in vastly different groups, and you'll be able to see that in the data when it comes available in phase 2. The build layout is as such, with 6 parts per build. What will be available to you? So the build layout in STEP or STL format. The print data, that's the in-situ print data, which Nat will go through for us in greater detail on the next few slides here. The pressure test data from that test of the picture that you saw already. And then some of the low-cost sensors that have been added to the printers are as follows: inline filament diameter, bed level, main current at motors and heaters, slicer settings, ambient temperature and humidity sensor, printer controller is LIMS, which has nozzle position, TMC drivers, reporting, etc. All right, Nat, I'll go ahead and hand this off to you for the next few slides here.
Thank you very much. Just getting to the right buttons and getting to the right place on the screen there, so I apologize. Okay, so it was, thanks Jennifer for that introduction and trying to get us, give us a chance to present to you and still keep it a challenge, but to show you what we've done. And then but we're really looking forward to you all's look through the data and the way in which you discover things. I think from the program standpoint, we started off with the challenge of just getting all of these different types of technologies to work together. I had brought forward to the program this device, this little box you see over here. Am I sharing? No, I'm not. So I need to be made the presenter, I believe.
I have the slides you put up, but if you want to slide or share something differently.
Oh, okay. Yeah, I'm going to need to, well, we can start with that slide. And then at a point, I'm going to need to jump over to present because I want to look through the files on my screen. It's easier to scroll through them. So what we had done was look through, based on the different classes of machines, and in this case, material extrusion, if we could find commonality. First, could we get any data from the printers whatsoever? And then the second part is finding commonality between that data and figuring out where those pieces are. So we started by connecting controllers. A Stratasys controller happened to have an MT Connect interface on it already. So that was nice, because the box that you see over in the bottom right-hand corner is a LIMS device, a Learning Integrated Manufacturing System. And then it's basically some of the acronyms float around like IoT and things like that. The fortunate thing about it is it doesn't need the internet, so it'll run all by itself, connect to your printer and grab some data. So the question was, if you have something there that can communicate, one, how do we communicate? So we started looking at the interfaces. A lot of the commercial printers use the Marlin technology. Anything touching Octoprint uses the Marlin technology, which was convenient because then we had a single interface to write against, and all of a sudden we could start connecting these desktop printers, which was great. So a Prusa, an Ender, or the Gigabots, and those are some of the things that we had touched. But many of the printers that are out there use the Marlin technology, because the question is, why would you reinvent it unless you were adding a lot of value on top of it? If you're using stepper motors, you're not closing the loop on that control, then the Marlin technology is a good first step for you to do that. So we developed code to talk directly to the Marlin printers via G code, really. You send over M codes to ask for data, and all of a sudden that started coming back. Now, once you said, okay, I've got an open connection to the printer and I'll see what the printer will give me, the second question is, what do you collect? So we started trying to take data and throw it into batches, right? I mean, there's a great thing about a material extrusion printer is you can get the XYZ location, which is awesome, because if you're grabbing any data, you've got context to exactly where you are in the build, while that's happening. And that's not true in like a laser powder bed, where you know what layer you're on, but you don't know where the laser's pointing, right? For their basic commercial interfaces they give you. You can add technologies on to find that, but they're cost prohibitive for most of the users. So in this case, as a user, you've got a lot of great data that can come right off the printers. So make, model, serial number, which is, it sounds a little silly, but sometimes that's really good, because you need to know what, control software rev you're running, which sets what data comes out, what the axes positions are, what layer you're on, and then what speed you're running, what's the extruder temperature, what's the target temperature for that extruder, what lot number, the filament, when did you order it. Some of these things are a combination of automatic data we're going to get, but we're also going to ask the operators, when did you order your filament, because that may make a difference in some of the data and some of your analysis on the back end. We'll ask them manually, what's the infill pattern, nozzle diameter. Again, some of those things aren't directly coming off all of the controllers, so sometimes you're going to have to do that. We added thermostats and humidity sensors right onto the platform, so we can get that. We also have the ability to grab the current from the machine, which is one of the things that the box gives us, not only as a computer to talk to these digital interfaces, but the ability to pull over some wires and sense additional environmental things that are not part of the controller's not sensing. So the other thing that we did was, looking across the controllers, I didn't want to lose any data. So for example, if you're doing pellets, there's a dryer. What's the dryer temperature? What's the target temperature for that dryer? There's maybe you have two extruders, right? And for your machine, you don't have two, so that's fine. Just, it'll be a goose egg, right? There'll be nothing there. So we made sure that the data itself is a superset of what's going on. And then while we're running, the box that's running, this LIMS box, also has built onto it some analytics that can be running. So one of the things, people may have 20 different printers and they want to know how they're doing. How am I utilizing my printer? Am I using it all day, or, is it down most of the time? So we do automatic production calculations even for these desktop printers, which allows you, for a small farm of printers, to really know exactly where you're at and what your utilization is. The other thing is to take and integrate your kilowatt hour usage. So what is your carbon footprint for that individual print? But it turns out to be a great diagnostics too. If your motors are starting to draw more current than you would by just a single current sensor that's clipped on the incoming power, you have some more data that's coming in there. And that may be with a simple clip-on current sensor, or and a simple thermostat for shot temperature and humidity. So that's the time series data into the buckets that we threw it in. What could we possibly get from the controller or the operator? What is LIMS contributing onto here? And then what's environmental data that we may be sensing with sensors added onto the system that the controller knows nothing about? To go to the next slide. So now with that data, then we're going to get that into some, this is the data that you're starting to see come out right now. So if we look at the the left side is going to be header information that comes out. So let me switch over to my display so I can just show some figures on the screen. Okay, I'm going to share, and I got file option. Can I share my screen? And now the presenter, and share. I'm sharing my screen. So share. Okay. All right. We have a PDF of this. I'm setting inside Visual Studio, my development environment, which will show you the structure of the reports that you're getting. There's a text file that's stored in JSON from these class structures that should be simple for you to be able to process and bring back in. That file extension is AMRP, which is the AMNOW report, right? So the goal would be is to take all of that data in those various classes and bring it into a single structure. This AMNOW report, which will keep track of the schema that we're using and the AMIP software version that we were running at the time we report, starts off with a lot of header information that lives on top of the report, which is build ID. So if you were running 15 different builds, we know exactly what build it might be, what was the software version of that was running on the cloud at the time, and some basic things that you can read here, which is the part name and who you are and whoever's doing the actual production. The AMNOW report conceptually was supposed to contain different steps of the operation. Now, in this case, the reports that you're getting will have a single step. It has the ability to say you printed it, and maybe you did some heat treatment, or you did some bath operation, or painting, or whatever you're going to do. All of those could be contained in different steps. You're going to see just a single step in yours, which is printing, right? Which makes sense. And then all that happens in the printing report, that step report for printing, is a bunch of data items. That data item will give you a idea whether it was manually entered. That's one of the booleans that's inside of here. And if not, what is the units for the data, if there's a units that's appropriate for that piece of data. And then if that data was captured by the controller and there were a series of data items, we call them time series data, right? If that piece of data, like the bed temperature, whether it's the X, Y, Z positions of the axes, if those were going on, then you want to be able to have that time series data as a list within the individual data item. So that was our new step for the program. Originally, we just had data items that were manually entered. And now we have a time series data, which is simply a value and a timestamp of when that happened. The rest of the context for that data item, the metadata, is contained within the AMNOW data item. So there's a series of time series. We only record when the data value changed. So if you don't see a time, you see 5 minutes between a set point change. Well, that's because it didn't change between there and now. The goal was to keep these files as small as possible so that we could do this program, store them in the cloud, and contribute every part build to the cloud, and not be overwhelming with, terabytes of data that nobody's going to look at or their eyes are going to glaze over. So that's the structure of the data that's inside of there. So what the operator will do, on site, is I'll go back to, we give them a tool that allows them to visualize what's going on in here. And again, this is way beyond it. I just want to show you where the report emanates from. Every time a job runs on this device, it stores a job history, which is that data. So for material extrusion, we could go down through here and you see my Prusa or Ender sitting behind me and jobs that they've run. And I click on that particular job that I'm interested in, and then I will generate a report, which has some areas that need to be filled out, like the build ID. What date did I calibrate this? And so we can fill those dates in. People create the reports, and then save it. So that's the burden to the person that's the operator on the floor to get you the data that you are receiving. And then when they save that data, it automatically saves out into an AMRP format, and that's as easy as we can make it for the supplier to be able to get that data. And that data inside this job history contains the time series data that's looking at. So if we take a look at a job history here real quick, and I'll look at my device and see all the job histories that I've pulled in, I can see that here's the Ender job history. So I'll double click on that. And now I could easily take a look on the device for the X positions, the Z position while that's going on. They're on the floor able to see this information. So they take from these job histories to create the AMRP. And that was the process we created on the program. Now let's take a look at what that document looks like as it's exported from that class structure into a JSON format. Again, step reports. Inside the header information that said who it was, I printed this as ATI, and there was my Edge software version. And now I start looking at my step reports, which contains a very first step of printing, and then it has a series of data items which are contained in an array. In those data items, we can see individual items here. Let's take a look down for something that has a something interesting in it. Let's and I just generated this quickly. So here's my machine address, the part file that I was working on, the control software rev that I was working on. And then finally, let's take a look at something that would be changing during the job. There's the part start, part end time as a date timestamp, layer heights that were calculated, wall thickness, and then finally we'll get down to, here's an example of printing temperature. So you can see the printing temperature is coming in Celsius, its data type is double, and here's all of the time series data that was associated with this, and every time it changed, we recorded it. So that was the series data. This is a printing temperature for the first extruder. Here's the printing temperature for the second extruder, which it didn't have one, so it got a goose egg on that. And then here's the target temperature, which was 200 degrees and 0. So you can see this time series data appears in the element series data with an array of any of the data that it received. And there will be some that do not have any type of information. Here's the build plate temperature, but the print target temperature one didn't have any data in it. And then the build plate temperature, we can see all of the times that it changed slightly within the run itself. And this, I didn't have my thermostat hooked up. Here's all the X position time series as well, Y positions, Z position. Here's the filament, which is being extruded by the Marlin printer. And then we were doing utilization calculations on the devices, and each one of those every minute is output, so you have all of that data, and then a actual value of the amperage, and we're doing kilowatt hour accumulations on there. So that's the basic structure. To come back to think about it, you're going to be presented with a report. The operations report will have a series of step reports, which we're only going to have one, containing data items with time series data inside of them. So, and then if we could switch back to your slide deck, I'm gonna, do I stop being a presenter? I'm gonna stop sharing. And if we can go back, Jennifer, to your slide deck, just to make sure that I'm covered the pieces of data that I put into there.
Yeah. Give me just 1 second to get it switched over here.
Sorry, didn't give you much transition time there.
No, that's okay. I think they needed to switch us as presenters anyway. Can you see it?
Yes. So again, think about just that next slide. There we go. So a single report file includes types and units that came from this history of the data that was in there. And again, you can see individual, for example, the layer height piece of data that's an example into here that was being recorded by the job histories that are on the files. So again, you have an AMRP. I will send you over a PDF of the structure of the data, which I think we already have handy. So that'll go out to everyone. And then we'll see what you can dig through in the data and find what you see along with the new testing data that's coming out. So this is exciting. So any questions? I guess they'll go into the chat window. I'm looking over there.
We can grab those at the end. I just have a few more slides here, but yes, please record your questions while they're top of mind, and we'll jump back into those in a little bit here. Just another, Nat alluded to the pressure series data that would be available from the testing. So this is just an example of that. The phase 2 data will include pressure versus time. All parts exhibited some leak over time, but you see the asymptotic leak decay here. So you'll have those and you'll be able to separate those into groups based on anomalies. Hopefully is really the goal there, and that's why this is given in phase 2, because hopefully you can understand and get there without this test, because ideally, if you think about it, it's preferred that you can see if there's a quality issue using the machine data and not requiring the test data, but this is a correlation to confirm what you see in the machine data, which will be available in phase 2 after you make your predictions. We'll provide data via SharePoint. So each person will nominate one person to have access to a SharePoint, and we'll organize it by build. So you'll have build 1, 2, blah, 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 until 15 plus, and you'll have time series data, which Nat just went over. So everything you just saw there, the sensor data with the example I just showed you, and then the pressure series data that, the sensor data, which I talked about earlier, and then the pressure series data, which I just showed you with the pressure decay. So key dates, the RFP was released last week. We are on the call now on the 12th. From there, we have tomorrow, on the 13th, the project call announcement and posting. There'll be a period of time where you can ask questions up until the 22nd. We'll respond to those questions within 3 days on the 25th. And then we'll ask for any submissions, full proposal submissions to be completed by April 29th. We'll do the award notifications by May 3rd, and we'll give about 10 days to issue those project agreements up until the 13th. That should be complete. And then you'll have from that time until the 24th, where we would ask that all of the data from phase 1, all your findings be complete, and there be a presentation to an evaluation team. And then we'll give about a month after that, where you would have access to data from phase 2, and there'll be another presentation. And then finally, we ask that the participants in this challenge also give a presentation at an America Makes event in the week of August 15th. What do you need to do to apply? So the technical content, it should be covered in what could be a 15-minute presentation. We'll do, you can present or you can submit that presentation in forms of slides or whatever, and then you'll have an opportunity to give that in person if you're selected or down selected from the pre-screening. And you'll address everything in the ASAL of 156, including how you will execute it, so a draft execution plan and a schedule, a list of the approach and proposed software tools, including description of off-the-shelf or proprietary tools. This is very important. We can't accept anyone who doesn't include this in their proposal. It has to do with us understanding any risk of royalties, etc., and making sure that we have access to the software, that the data is useful, or at least there's a way to make the data useful for the people who are seeing this and for the greater community there. So please describe that, what you plan to demonstrate, experience you have working with material extrusion, artificial intelligence, and data analytics. It's not you must have experience with all three, but it is very helpful if you're familiar with the process. And of course, it's helpful if you're familiar with AI and data analytics tools. Programmatic parts of the proposal, please tell us the participating organizations. If you could identify one person from the team to access SharePoint and download the data. Indicate your willingness to present at an America Makes sponsored event in that August timeframe that we talked about. And there will be a list of additional administrative information that you'll have to fill out, and that'll be part of the RFP. And you'll all receive a link to that RFP when it goes out tomorrow. The selection to enter phase 1. So this is the criteria that we'll use to evaluate those in all these proposals. So the approach will be 40%. So the approach should include correlation of machine and sensor data, identification of process anomalies, correlation of phase 1 and phase 2 data, identification of anomaly location. So what is your approach for finding those things and exploring those challenges? Draft execution plan and schedule, please include that for 5%. Proposed software or tools, including description of off-the-shelf proprietary tools. Like I said, it's a must-have, but it'll also be rated based on uniqueness, description details, and computing efficiency. And then also your experience working in those 3 areas. The RFP website and the myamnow.com website that Ashley referenced before. So that is the conclusion of our slide deck. And at this point, we could go on to Q&A.
Thank you, Jen. I do see a few questions. If you do have any questions, please drop them in the Q&A and we can go to those. The first question, Jen, can you please tell what the anomalies are? Is it a mechanical response, like fatigue response?
I don't think we want to tell you that. Am I wrong, Nat and David?
That's correct.
That would be my answer too.
It's an anomaly in the data.
I think you'll find it, and that's kind of part of the challenge.
And the next question is, will we receive all the sensors and data for model development?
We will, as we recorded, either during the printing operation, which is where the anomaly data would be. It is a combination of data coming from the controller, data coming from the environment, and information that was typed in by the operator. The data typed in was typed in properly, so we don't think that's human error in typing that would be the anomaly. So that's one thing to rule out. But the rest of it, it could be anything from environment to actual printing, anything observed by the controller that is fed in. Those are opportunities for anomalies. You will receive all of that data in the AMRP. The file itself contains that data and contains evidence of the anomaly. Not trying to be nebulous, but I want it as a challenge, right?
Yes, absolutely. Does anyone have any other questions? You could either type it in the chat or you can raise your hand and we can unmute you. Any other questions? I don't see any coming in. Jen, Nat, anything else to add?
Yeah, I was just gonna ask you, Ashley, could you describe the process for submitting questions after the RFP goes out, if they have scope questions?
Yes, absolutely. So questions regarding the challenge, you will submit them to amnow@ncdmm.org. We will gather all of the responses and then they will be posted on the website. All of that information is also on the website with the key dates, so you guys could see that once the link goes out. I did see a couple questions come in. Jen, let's see here. Can these sensors be able to detect failure modes like warping, nozzle clogging, part collision avoidance?
Yes, is a short answer to that. David, do you want to add anything?
Yeah, the ASAL provides a specific list of the data that we'll be providing, but the general answer is yes. The purpose is that the analytical data will inform you of what the anomaly is. You have to find it. But specific to this question, not all of these are part of the data sets, and they're not necessary. We are giving you the data you need to find the anomalies. And they'll be listed, the categories will be listed in the ASAL.
Thanks, David.
Let's see what else we have here. Can we
Can-
have labeled data for the anomalies? Yes, that's what you will receive, Raul. And are you looking for this problem from pure quality assurance perspective or also considering security?
Could be either. I think our approach has been mostly around quality assurance, but I don't see why it could not be used to detect a security issue.
Yeah, I think that depends on the application of this particular anomaly. It depends on why one would build a part to accomplish this goal. Again, sorry we're being so vague, but the mission is to look in the data and figure out what the anomalies are.
Thank you, David. Any other questions? I do see a question that came in. It says, any possibility to find residual stresses within the part using this data?
I think it's best to wait to see the ASAL and you'll see what data you're getting.
Yes, and to piggyback on that, so like Jen mentioned, the statement of work along with additional documents will be available for download tomorrow. So as you guys go through those documents and you have any questions, please jot them all down and submit them to AMNOW at ncdmm.org, and we'll get those answered and posted to the website.
Yeah, I'm sure more questions will emerge after the ASAL is released, and then we'll be happy to answer them.
Yes. Any other questions from any attendees? Jennifer, Nat, David, any last items from you guys?
Not for me.
Sounds good for me.
Me also.
Awesome. Let me just make sure there's no other questions that came in. Okay, so that will wrap up today's AMNOW Polymer Challenge Industry Briefing. I would like to thank Jen, Nat, and David for joining me today. Like we mentioned, the request for proposal will be available tomorrow, April 13th, and can be downloaded from the America Makes website. And that will be provided via email when it's available. All information regarding the RFP, dates and deadlines, resources, frequently asked questions, this can all be found on the RFP webpage. Like I mentioned, if you have any questions, please send them to AMNOW at ncdmm.org. And again, this can be found on the web page. That second link that was on the last slide that Jen was sharing, that is the link to the AMNOW AMIT platform. This is where you would register as a supplier to participate in the AMNOW program. And also on that site, there is a resource page with additional information regarding the AMNOW program if anyone's interested in learning more. So with that, thank you all for joining me today, and we look forward to your submissions.
Thank you all.
Thank you.
Thanks, everyone.